Welcome to Elektor Engineering Insights, the show that puts your engineering challenges to the industry's experts. I'm your host, Stuart Cording, the electronics reporter. The world of test and measurement has changed dramatically over the years. Back in the 90s, you needed a trolley to move a spectrum analyzer around the lab. Today, the one integrated into your oscilloscope probably meets most of your needs. But does test equipment need a screen at all? Increasingly, we're seeing headless test tools using a laptop or tablet as their screen. But what is the performance of such tools? And do I want to replace my trusty but beige kit with something that fits in my pocket? And what are source measurement units used for? And what would I test with one? To find out more, my experts for this episode are Mark Edwards and Matthew Middleditch from AIM-TTI and Ben Nizette from Liquid Instruments. So let me bring in Matt and Mark first. Hi there, Matt and Mark. How are you doing?
Hello,
Hi there.
Very
Good,
well.
cheers.
So Mark, tell us a little bit about yourself and your role at AIM-TTI.
Okay, well, I've been with the company 37 years, so
Wow.
I've been in the test and measurement industry for a long time. But I'm the sales director here at Thirlby Thandar Instruments, as many people know us. But AIM-TTI is our brand for marketing.
Super. And Matt, tell us a bit about what your role at AIM-TTI.
So I'm a senior development engineer here and also the lead designer on the SMU project that we're going to talk about.
Excellent, super. Well, thanks for joining us. Stay in the show there for me for a minute as I move over to Ben. Hi there, Ben. How are you doing?
G'day, Stuart. Yeah, I'm going very well, thanks.
A nice Australian greeting. I thank you ever so much for staying up so late to talk to us. Maybe you could introduce yourself a little bit and explain how you help customers at Liquid Instruments.
Certainly. So I am Ben Nizette. I'm the Director of Product at Liquid Instruments, and we make reconfigurable test and measurement equipment that I'm going to be talking about today. I've been around Liquid Instruments since we were founded about 8 years ago now, so we don't have the history and the heritage of AIM-TTI, but yeah, we're looking to innovate in the space in a similar way to them, and yeah, hopefully to share some of that with you today.
Exactly. A 37-year career is planned, I think, on your side too.
Either that or I'll be on an island, living the startup founders, post startup life or something. Yeah.
Super. Okay, you stay there too, and we'll be back to you again shortly. So, where do we go now? So, this episode is sponsored by Volterra. Founded in 2013, Volterra focuses on additive electronics manufacturing with their V1 multifunctional PCB printer. Since its launch, the V1 is now deployed in over 80 countries, supporting developers and educators with their rapid prototyping needs. Fitting easily onto your desktop, the V1 can print and assemble a simple PCB within an hour, allowing you to quickly iterate your design several times in a day. The V1 and its accessories are available through the Elektor store using the link below. Now, I have fond memories of pushing test equipment around the lab of my first employer, building test setups for crystal oscillators. Today, so much has changed. Not only is equipment smaller and easier to use, it can be easily interfaced with the PC for automated testing. Because of this experience, I have loads of questions prepared for my guests. However, this show is for you engineers out there struggling with your designs. So regardless of where you're watching, post your questions and comments during the show using the chat function on YouTube and LinkedIn. Or you can use Twitter with our hashtag ElektorEI. And we'll do our best to get you answers or guide you to some resources that might help. So with that, let's get back to Matt and Mark. Welcome back.
Hi.
Now, one of the things I was looking at the source measurement unit, and it looks very similar to a power supply. So most engineering teams, they'll have a bench power supply and a multimeter on their desk. But you've got this source measurement unit, which is often abbreviated to just SMU. How does an SMU differ from a power supply combined with a multimeter?
Well, you're correct, Stuart. I mean, our decision to make an SMU came about because as a manufacturer of precision laboratory power supplies, we were often asked for a very agile power supply or a power supply that could log information very quickly. in our initial investigation into how we could achieve that, we came to the decision that a source measure unit that's already available in the market technology, we thought we could improve on and bring to more people. And a source measure unit, due to the fact that it both sources and measures the information and feeds that back through its internal system very quickly, you can move the power supply's voltages very, very quickly and stably, and at the same time synchronize that with a measurement result. So a precision linear power supply typically will only measure 3 or 4 acquisitions at a time, whereas the source measure unit, due to its speed, can make many measurements, 200 microsecond measurements.
So at its core, an SMU is like a voltage source, but it can also be a current source. And in that single unit, it has this precision measurement capability like a multimeter. What kind of applications or components require the use of an SMU?
Well, component characterization and material test are the 2 main applications. Often quoted example for an SMU is for characterization of a diode. This requires a bias voltage and a measurement of the current, both in the positive and negative. So from the leakage current right through to the switch on point with a wide range of voltages. But Matt can highlight you on a few more of the applications.
Yeah, so really, primary things you might be looking at materials testing and characterization. You might be looking at battery testing. SMU is a great instrument for battery testing because it's important for everyone to note that this is a 4-quadrant instrument. For those that aren't aware what that is, basically it means it can source and sink. So you can also then source positive voltages or positive currents and negative currents and voltages. So for battery testing, it's a real benefit because you can not only charge a battery under test, but you can also discharge that battery in with one instrument under the same test conditions. It may also be photovoltaic cells or solar cells, but an area of interest, like Mark has said, for us really is semiconductor testing and component testing. So when you're looking at a diode, for example, which is a really nice component to test with a SMU into doing IV sweep, for example, because you get these simultaneous voltage and current measurements for each source level you set. When you sweep across a diode, you can actively measure the voltage and current as you sweep across that diode. Going into a bit more detail with this sweep, it doesn't just have to be a standard sweep. We offer logarithmic sweeps, linear sweeps, dual sweeps, so it can sweep up and sweep back down again. And also a very interesting one for component testing is a pulse sweep, which if you've got a component that might suffer from self-heating, for example, as you're doing this test, the component gets warmer and it affects your readings that you're getting. We can offer this pulse sweep where actually you do a normal sweep, but after every step, you can pulse to a set level to allow that, for example, in this case, you might pulse to 0 to allow time for that component to cool again before you do the next set level. So it's a really useful instrument for doing that kind of testing on components and semiconductor devices especially.
So I guess those are the sort of tests that are typically used by companies developing sort of power supplies or power converters, sort of motor inverters. Would that be the case, or is it more wide-ranging than that?
It's certainly more wide-ranging than that. One of the difficulties in developing this product has been that there's so many applications you can use it for, which makes it very difficult as a designer to really, we'd rather sometimes have a specific design that a requirement that you have to meet. But when there's so many different components and areas of interest, it makes it very difficult to design one product that can do it all. But SMUs really are a product that can do most things. There's always going to be limits on power. We've pushed it pretty far with this instrument with 25 watts and 3 amps. It's been a challenge, especially with how small the instrument is. We go on here just to show. This is the size of it. It's
wow. Okay.
Compared to a lot of other SMUs, this is significantly smaller. But if I can just take a bit of time to explain our PowerFlex technology, which we've taken from our power supplies. This is something we're not aware that any other SMU manufacturer does. So what our PowerFlex technology allows for, if you can see here, a conventional SMU would have a very rectangular power envelope, whereas we've gone for this PowerFlex technology, which actually allows us to have basically the instrument's maximum power across the majority of the voltage range. If, for example, we took a standard conventional 20-watt SMU and you ran it in the 20-volt power envelope range, you might be limited to, say, 20 watts, which would be 1 amp, so 20 volts at 1 amp. If you were to then drop the voltage to 10 volts, one might expect that you could get 2 amps out of it. But that's not the case in most SMUs. In our SMU, you can do that. So this power flexing allows us, as we drop the voltage, to actually increase the current capability. You might have noticed I said the majority of the range, because you can't, once you drop below 8 volts, for example, say 5 volts, you can't obviously achieve the full power because we are restricted to 3 amps. So, 5 volts at 3 amps, you're talking 15 watts. We can't push it any further than that because we are already limited. But that's essentially what the PowerFlex technology allows us to do.
Yeah. Excellent. Now,
why you'll see we only have a single model in our current lineup, and some of the more established people have multiple models covering different voltage and current ranges because they don't have that PowerFlex capability.
So, so one of the things I was sort of looking at that, and obviously there's we've already seen that there's obviously lots of different configuration capabilities with the voltage output, the current output, the measurement options. I imagine it must be quite complex to set it up. How can I sort of ensure, for example, that as I'm sort of reconfiguring it, I don't all of a sudden have the voltage go outside a range that my device under test can handle?
Well, the SMU, to make it easier to set up on the SMU 4000, we do have predefined easy setup modes, which enable you to go through, at the presently I think it's 8 setups, for defining the outline parameters for any setup. The customer can then set their own limits and their own levels within that setup.
Yeah, we've certainly done everything we can to make the setup as easy as possible for the user. These presets are really, these easy setup presets really are presets. They're configurations that we believe best suit that application, but they're not, well, they're easily configurable after that. So once you start to build an understanding of how the SMU works, you can move on from these presets to actually start setting individual levels and go far deeper into the instrument. It's almost a way into the instrument, along with our sort of context-sensitive help that we offer. But in terms of limits, if you're actually interested in how to set a limit, obviously with the source voltage modes and source current modes, they both come with a limit associated with that you can set quite easily from the front panel. We also have many protection limits which will trip if you exceed or breach those limits.
And once I've sort of found a preset configuration and modified it to my needs, can I save that as well to recall later? Yep.
So one of the interesting things or bits that we sort of developed, it wasn't initially the plan at the start, but as we were developing it, we found that, because there's so many settings, we don't want to limit people's flexibility with this product and restrict them in certain areas. We want to make it fully flexible. And so when you've created all of these settings, you really want to be able to store them. So yeah, you can store setups, but on top of that, we also have a sequence mode, which once you've created, it could be a whole series of setups, you can actually import these setups into a sequence mode. And that sequence mode allows you to play through these setups, but also you can use the DIO control for jumping to different setups, for example. You can also have different conditions that would result, say you're doing a measurement, it might have been just a voltage measurement, but you can add a condition in the sequence to say, if the voltage exceeds a certain level, jump to this step or this step. So yeah, not only can you create these setups, but you can also go much further with the sequence mode as well.
Now, I was also looking at the specifications for the SMU 4000. I mean, it's pretty impressive. It is plus minus 200 volts, plus minus 3 amps, and 25 watts of power is possible. and obviously you look at those big numbers and think, oh, that's great, that's for certain types of application, but how does it perform at very low voltages and very low currents?
Well, it's interesting you noticed that, straight away, because obviously with our background in power supplies, it was it was a very big interest of us to go for as much power as we could and as much current as we could, because that is our, historically our background. It's been a difficult learning curve for the very low voltage and current measurements, because it's I wouldn't say completely new to us. We've done DMMs and bits before, but it's a difficult area. But we're very proud that we've managed to get the voltage range down to 20 millivolts and the current range down to 200 nanoamps. And we've tried to offer many other additional benefits, such as guarding on the rear terminals. We've added 2-wire plus guard on the front terminals. So if you want a guarding on the front terminals, you can add, when you select the 2-wire plus guard, the high sense terminal becomes a guard terminal. And it's all, when you're looking at the very low voltage and low current measurements, it's not just about the instrument, unfortunately. It's about how the user applies that instrument.
Yeah.
Once they're outside of the instrument, it's up to them to select the right connections and provide the right guarding, and which we've tried to do everything we can to make that easier for them.
Yeah,
we're very keen to get feedback on applications and low voltage measurements and how people are using it and the problems they're facing. Because we want to both help them to cure their problems, but more importantly, we want to learn as quickly as possible. So any questions anybody has on possible applications or problems they see, we'd be very happy to share.
Super. Well, hopefully I can see there's a few comments coming in at the moment into our forum, so we'll pull out some of those later and pose them to you directly, see if we can get some answers for our viewers. Now, one of the things with these types of test tools is there's a need to sort of change the voltage or change the current very rapidly in order to make us, do some sort of step testing or double pulse testing and things like that. What's the speed like of the SMU when it comes to implementing those types of tests?
Well, this probably with any SMU development has been a real push, because like Mark mentioned at the start, with our traditional power supplies, we're looking at a very slow, stable output, whereas an SMU is a fast, reactive output. So we're really pushing for sub-millisecond response times. So, for example, the source voltage we spec typically around 300 microseconds, regardless of range and setting, to reach a stable value, a stable level. Sorry. Along with that, and our measurement speed is then followed up at 200 microseconds. So you're talking, like I said, sub-milliseconds to not only reach the level and be stable, but also then to get a measurement at that level as well, ready to move on to the next level. One of the features we actually added, and a lot of people already have, is a measurement delay. So you delay the measurement until it's stable. But one thing we did with our auto version of that is to actually look at the measurements at a very fast rate, actually a rate beyond what the customer can see, to check when we believe that measurement, or when that source level has actually reached stability, and we can then give the first reading back, because
right.
that delay can actually have significant effects on your measurements. Basically, if you measure too soon, then you're going to see your rise time or your rise, which you don't really want to do. If you measure too late, you're wasting time. So it's trying to optimize that auto delay to give you exactly when that source level has stabilized after 300 microseconds.
Yeah. Now, one of the other things that I see sort of increasingly growing is this need to automate sort of test equipment and to do maybe sort of batch testing of components as they come in before you put them into a manufacturing environment, or I might want to test a whole bunch of different components as I'm selecting them for developing an application. Does the SMU 4000 also support some sort of scripting or API?
It fits very well into that application, and component testing with using a matrix. I was talking to a switching company just last week that you've utilized in the past many SMUs into test systems for testing both passive devices and semiconductor devices. And they're using a switching matrix combined with the DO interface on the rear of the SMU to switch and test multiple components, or in test systems where there is a lot of different voltages and levels being tested, where you're switching a single channel or a single device to do multiple levels of test or on multiple points of test using a switching matrix.
So, and in that case as well, are there certain situations where I might want to have two SMUs operating sort of synchronously or in parallel to test a component? And if that's the case, how do I go about doing that?
Yeah, so very early on, we were very keen to think about how you might test, for example, a FET, field effect transistor, because we're very keen on semiconductor testing and that here. It's so very early on, we almost considered having an auxiliary channel, but we found actually we could provide a customer, two instruments and find a way to connect these instruments together and synchronize them together. So we came up with what we call a link adapter, which connects the two DIO ports of the two separate instruments together, as you can see on the slide here. And the idea of this is that the global trigger of both instruments is then connected together. So one SMU effectively handshakes with the other. So you can set them both up to do, say, a sweep across a FET where one instrument is connected across the gate source and one's connected across the drain source. You can sweep both instruments and it will synchronize both instruments to, in this handshaking scheme in order to sweep across both simultaneously, basically. You can then export all these results into our, export it into Excel, or you can export it into our test bridge software, SMU test bridge, and review and make analysis of those results.
That's a good point. I was also a question in my mind, because when we look at test equipment nowadays, even the smallest, cheapest piece of test equipment has a color TFT display that seems to be par for the course. And but the challenge is obviously, although it's a nice color display, sometimes maybe like an inch or two in diagonal, it can be very difficult to analyze the data. So how do people go about then exporting the data to a PC and monitor their measurements that they've made remotely?
We expect that most customers using the instrument in a benchtop application, certainly in the initial setup or where they're taking lots of data, will use the test bridge software, which is a free of charge piece of software we provide. This enables the customer to make many of the complex settings and store those settings, but more importantly, to be able to easily analyze the captured results, because obviously you're talking about many data points that you can both graphically display or define as a graphics file.
Super. Well, thanks ever so much for those insights. We've got a few, as I said, a few questions from the audience which they want to pose to you. So we'll join you into the fold later when we have our roundtable discussion and get some answers for our audience there. So thanks ever so much, Mark and Matt. It's been great to get the insights there on source measurement units.
Thank you.
So now we come to the exciting part of our show, our giveaway. Firstly, congratulations to our previous winner, that's Wojtek. Your Cytron MakerPi RP 2040 board is on its way, and that was a board we gave away last week, which is great for developing robotics applications. Now, to extend our thanks to you as loyal Engineering Insights viewers, for this episode I have an Andonstar digital microscope. If your eyesight is failing you like mine is, perhaps it's time to take a closer look at a digital microscope. Get up close and personal with those hard to read components on your PCBs, and you can even keep a copy of the images for posterity. For your chance to win, simply visit the link shown below and enter the keyword multifunction. That's the keyword multifunction with your entry. And we wish you all the best of luck with your competition entry, and hopefully you'll be our winner, and we'll announce that in the next show. Now let's bring in Ben from Liquid Instruments. Well done for staying awake, really impressed.
Thank you.
Now, there's plenty of test equipment on the market. There's the big players, the small issue you saw on the market to address those sort of test and measurement issues.
Yeah, there certainly are lots of established players in test and measurement, but the rate at which general purpose test and measurement equipment has been evolving isn't nearly as fast as the rate at which the stuff that it's supposed to be testing and measuring has been evolving. Yeah, a lot of the technology that we use day to day did not exist 10 or 20 years ago, but certainly oscilloscopes and things have existed much longer than that. So we found that that became even more significant, even more serious, if you were trying to do something that was a bit outside of kind of the day-to-day, something that was a bit niche. If you were an innovator, then your choices were really to build some complex circuitry around a standard oscilloscope or a wavegen, or you would then go all the way to something like a PXI or VXI chassis from National Instruments or someone like that. And if you were doing that, you had all the flexibility in the world, but your time to first measurement was potentially, weeks or months. So what we really want to do is to empower innovators to make kind of interesting, unique measurements, but quickly.
Now, today you've got three sort of products in your MOCO family, and they all sort of follow a very similar structure. Can you provide us sort of an overview of the structure of your hardware and your overall design ethos for those tools?
Yeah, absolutely. So in fact, you can kind of see in my background here, we've got MOCO Lab in the middle there, if I can work it out. That's the OG. We launched with that back in 2015, ostensibly for kind of research environments. And then 2021 was very, very busy for us because we brought out MOCO Pro at the top and MOCO Go at the bottom to bookend MOCO Lab in terms of both cost and capability. But fundamentally, all three of the MOCO products, they digitize the signal as quickly as possible, and they output they move as much of the DAC side into DSP as possible as well. So the hardware is as simple and as general purpose as possible, and all of the instrumentation moves into software, but not just any software. It runs in an FPGA, a field programmable gate array, inside of the MOCO devices, which is a contrast to more traditional software-defined instrumentation, where the software might be running on your laptop and data's being shuttled backwards and forwards, supposedly in real time, but never quite. So yeah, that's the core of it. You have the flexibility of software defined because you can swap instruments on the FPGA at any time, and we can talk about that a bit later. And also have the performance of dedicated single box equipment because the software is on the device. Like when it's running as an oscilloscope, it is a single box oscilloscope. It's just one way you can press a button and switch it to be something else.
Now, as I said in the opening, one of the things everyone will have noticed from the picture behind you is that nothing has a display. So what provides the user interface, and what sort of device do you recommend people should use in order to configure the tool?
Yeah, absolutely. So when kind of re-examining test and measurement equipment from the ground up, we looked at touchscreen displays, and you mentioned before, the little 1.5-inch TFTs that are on the front of a lot of things. But at the end of the day, we were never going to be able to build something that is as nice to work with as an iPad or as a laptop. The thousands of dollars devices that have had many tens of millions of dollars worth of R&D behind them. So we just lent into that. All of our MOCO products have a desktop app that can be used on Windows or Mac. The higher end ones have a beautiful iPad interface as well, which means that you can walk around your lab. You can stand and take your measurements in one place and control it from somewhere else. And actually during COVID, this was massive as well, because it meant that people could completely seamlessly, like this is network native, so they could completely seamlessly take measurements from their offices in isolation or even from their homes when they needed to.
Now, one of the other interesting things about the Moku hardware, when you look on the website and see how the tool is constructed, you've got, it depends on the device, doesn't it? And it depends on the hardware, but there's somewhere in the range of 10 plus different measurement capabilities or tools. There's not just measurement, isn't it? Because they can also output signals as well. There's signal generators, voltage outputs or power supply type outputs as well. What's clever about it is that all those different tools that are integrated in there, they can be linked together into a complete testing system. And that's something that would sort of like normally require several pieces of equipment on the desk.
Yeah, absolutely. So as you say, there's 10 plus instruments. We've got things that view like oscilloscopes. We've got things that generate like waveform generators. And we've got things that do both at the same time, like filter boxes and PID controllers and things like that. But when you're starting to reconfigure an FPGA to be an instrument like we are, the natural question is, well, why only run one at a time? What can we do here? So some of our products splits the FPGA into 2 pieces, some into 4, and allow you to run up to 4 pieces of instrumentation simultaneously, all on the FPGA, so real time, lossless, low latency data interconnects between them. And yeah, again, you kind of get the best of both worlds. You get to set up a test rack now, not just an instrument, in a box dynamically.
So I think that application that you mentioned there, the PID control, I think that's one of the cleverest things, because that's something that's not very easy to implement in the laboratory, even if you had different types of testing tool. If I recall correctly, you've got a demo that you're able to show us of the Moku in action, and also running that PID demo.
Yeah, that's right. I mean, usually I would run this demo live, but it's midnight here in Australia, and frankly, I didn't feel like staying in the office quite that late. So I pre-taped something a little bit earlier today. I hope you and your audience will forgive me. But if you can pull that up into the stream, we can have a bit of a look at using not just PID, but like a couple of instruments in Moku just to show you what I'm on about.
Okay, so let's take a look at that.
Open up the oscilloscope here. So as I press that, the oscilloscope logic is being deployed down into the Moku Pro here, and it's now become an oscilloscope in a very real way. So we're getting the flexibility of a software-defined instrument just by being able to say, I want an oscilloscope now, but it's now running in this box at up to 5 gigasample sampling rates and so on, so very high performance. And you can see here that the input that I've got to this at the moment is just a noisy sine wave. It's actually a slightly unstable clock with a bunch of electrical noise on it afterwards. So what if we want to look at the stability of the clock, actually characterize the oscillator? Now, obviously here, there's too much electrical noise to do that. Like we can sort of zoom around and look at a few different things here. But at the end of the day, there's a lot of noise going on there. So what can we do about that? Well, we can do things like look at a spectrum analyzer and just have a look at our tone, our 10 megahertz in the frequency domain. There it is, nice. Still not going to help me a lot with the characterization. If there's any kind of drift in this frequency, I'm going to want to zoom right in and kind of record that over time, record the peak position over time. So because I kind of want to look at it in the time domain, maybe it makes sense to go back to the oscilloscope, but I'm going to do something a little bit tricky with it. So I just went into multi-instrument mode. For Moku Pro here, multi-instrument mode, you can think of it like a 4U rack, where you can slot up to 4 different instruments in next to each other and then like wire them up however you want. In this particular case, I've just got the FIR filter builder sitting in front of the oscilloscope. I'm only using 2 of the 4 slots. And if I deploy that now, this is being reconfigured to put a filter on the front of my oscilloscope. So I can open this up. You can almost think of this a little bit like the AC-DC coupling on the front of a traditional oscilloscope. I mean, we've got that as well. It's a bit different because AC-DC coupling is in the analog front end, and this is a digital thing. What this allows you to do is to look only at the frequencies of interest, but still look at them in the time domain if you want. So here I'm going to go, okay, the frequency response, I could just choose to sort of low pass all the high frequency stuff or whatever, but I want a band pass filter here. I'm happy to have the maximum coefficients, which gives me the best quality response, but a longer latency. And if I go across to the magnitude and phase, I can drag around the corners of the bandpass filter here. So, the frequency that we're looking at is 10 megahertz. So let's just do like a little window around 10 megahertz, just tap and do something like that, 10 megahertz. There we go. So there's like a little bandpass around my 10 meg now. And if I go out and into the oscilloscope, we should see a much more stable sine wave. There we go. We do. Much lower noise, much, much prettier. So that's kind of nice, but we're actually still not really able to see any kind of instability in the time domain, right? We can zoom in on the zero crossing that is after the trigger point, and we're looking for like horizontal jitter here, which might indicate that our 10 megahertz isn't precisely 10 or it's not stable. And there's a bit there, but we can't really tell how big it is, but also whether it's just residual electrical noise or whether it's from the clock itself. So the nice thing about MOCU is that you've got access to the right tool for the job. You don't need to force an oscilloscope to do something that it was never really designed to do. And the right tool for this job is the phase meter. So despite its name, the phase meter actually measures three things: phase, but also frequency and amplitude of a single tone. So you can see here that I've already configured input 1 there to be locked to 10 megahertz. So the tone of interest, and there could be many in my input signal, the tone of interest is at 10 megahertz. I can just type that in there, 10 meg. And then it gives me frequency, phase, and amplitude readouts, like that. And then if I tap there, I can look at the time history of these measurements. And in this case, the time history of the frequency measurement shows me very clearly that there is an instability. There's a sinusoidal kind of modulation on top of my clock signal here, plus or minus about 10 hertz in 10 megahertz, or it's like 1 part per million, 2 parts per million overall variation. And it's varying around at about 1 hertz. So this is super useful to me. This is the kind of thing that I can then take back and look at why. I can either fix my oscillator or add some more filtering or whatever else I need to do. But we couldn't see this. We would have had no hope of seeing this on like an oscilloscope. The great thing about MOCU, you've got the right tool for the job. So, because this is a whirlwind tour, I'm going to switch very quickly now over to my computer. There we go. And here I'm now connected to this, to the MOCU Go that is sitting next to me here. And I'm open in multi-instrument mode here again. So multi-instrument mode for MOCU Go only has 2 slots. It doesn't have 4. It's a smaller and cheaper device. It starts under 600 USD. And in the first slot there, I've got Cloud Compile. So MOCU Cloud Compile is a feature that allows you to write your own custom code and run it in the FPGA alongside our instrumentation. So that can be a full new instrument if you want. In this case, I'm using Cloud Compile as kind of an I/O driver to decode the distance information from the ultrasonic sensor down the bottom, and then encode my speed information to an ESC, to an electronic speed controller, that will control this fan on the top. So if I open the FRA, I'm going to now try and do some system identification and see what the frequency response of this plant is, of this helicopter. Let me do that now. So I hope you can still hear me over the fan noise here. But you can see that I'm driving a swept sine wave into the plant here, and I'm measuring its response. As the frequency gets lower, the amplitude gets higher. You can imagine that that's expected. You would expect this to respond better at low frequencies than highs. You can hear it's just restarted the sweep. So it's now restarted at, I think, 20 megahertz was the high end of my sweep, and it's coming back down. And if I just let it finish this sweep only and then turn itself off, we can have a look at some of these features of the Bodhi plot that it has just given me. So I'm just going to zoom in like this. There we go. So it's finished the sweep and turned itself off. It's a little bit abrupt, but it's fine. So you can see, we'll drag out some cursors. You can see that above about 3 hertz or so, it's noisy because I just did that sweep quickly. Normally you'd spend a bit more time on it. But above about 3 hertz, there's about a 30 dB attenuation. And then as it gets up towards 1 hertz, it's only about minus 10 or so, which is nice because that allows us to do the second half of this. You can use the FRA, the Bodhi plotter, to characterize filters or whatever else you want. But in this case, one nice use of it is to then look at the frequency response of the plant and compare it to the frequency response of a PID controller like this here. So if I open up my PID controller now, I can now design a frequency response for my PID controller that is complementary to the frequency response of the plant. They cancel each other's weaknesses out, right? So we saw that the plant itself had a big attenuation above, basically above a couple of hertz. So what we would probably want to do then is to turn on a differentiator. Just going to turn off that for a second. Turn on a differentiator that gives us a bit of extra gain at some of these lower frequencies, some of the high frequencies, sorry. but I don't want infinite gain or really high gain, because then I'm going to start amplifying noise, so I can turn on my differentiator saturation and then like drag around some of these little handles and things so that I can say, all right, the maximum gain that I want is only about like a 12 or 15 dB boost, something like that. Now, I'm not going to sit here and tune a PID controller. It's not a great use of your time or mine, but that's how you do it. You just drag around handles to design the frequency response of the PID controller you want. If that's not your bag, you can press this advanced mode button and just directly enter your PID controller gains as well, KI, PK, KP, KD. But I find, particularly when paired with the frequency response analyzer, looking at all of this stuff in the frequency domain is the right way to do it. It's super useful. It's really nice. So with that said, I'm going to go back to the live portion and we'll keep on going. Thanks.
There we go. Super. Thanks very much. I'm scared for my job now. Presentation skills there. No, it's really, really good to see it in action. And I think the really nice sort of clever thing is that, as you said, you can sort of plug all the little bits of the testing capability, all of the functionality together and link them all as you go along. One question that arose out of that was that you were saying in the last section there with the PID controller that you can actually sort of create your own software for the hardware in the FPGA. Do I need to be an FPGA developer in order to do that and sort of compile all of the Verilog code or something, or how does that work?
Yeah, so the Moku Cloud Compile, it does take FPGA like HDL, like VHDL type code. We recognize that unless you're an FPGA expert, that can be hard, but there are excellent tools that can help you code in Python or in MATLAB and do some exports. And believe it or not, in about 2 weeks from now, I think, a little bit more, I'm going to run another webinar just from Liquid Instruments ourselves, where I'm going to describe how to use ChatGPT to write your code for you. It does a surprisingly good job.
I was wondering how long it was going to take before we got back to the topic of AI in the show today.
Right.
The other question as well that we talked about with Mark and Matt was this topic of automated testing, and you also mentioned earlier that during COVID, the platform as it is implemented today allows that remote control and remote testing. What sort of support do you provide for sort of repetitive automated testing and the collection of results for analysis?
Yeah, super important. I reckon that the majority of our customers probably use the desktop app and iPad to kind of get a feel for their system and explore it. But then when it comes to validation, they're going to fall back to Python, probably, maybe MATLAB or LabVIEW. And we support all of those languages and many more. We use just standard API structures under the hood. So it's very easy to put your own little JavaScript widgets on it or whatever else you wish. But yeah, probably Python is our most commonly used API. And we have piles of examples and some really clever support people as well who can give you a hand if needed. So
I've forgotten what I was going to ask. I had a special question that popped up in my head and it's now evaporated. No, that's what I was going to ask. We sort of started off talking, or at least I started and introduced the show talking about the fact that we've had all that traditional equipment, all those beige boxes that we typically have in the lab. Are you seeing lab technicians and the people who sort of are responsible for laboratory equipment looking to sort of downsize the amount of equipment they have and replacing it with a Moku, or are you seeing more traction in, for example, education and research labs?
Yeah, well, I think a lot of the motivations track to both of those places. So we do sell a lot into education. That Moku Go down the bottom there because it's quite cheap. That's being used in hundreds of educational institutions around the world, because you can teach first year circuits, you can teach third year power, you can also teach like the control systems course, you can teach communications because we've got spec ans, we've got things that do modulation and demodulation, you can teach your RF courses off it. So yeah, all of a sudden you get to use one physical lab space for all of your courses for maximum flexibility and so on. And certainly that's true in some of the bigger companies as well, where they're looking to potentially replace like tester racks that could have 7-figure price tags. That could be north of $1 million because they have to have all these different boxes and then a big kind of switching matrix at the bottom to connect them all in different ways, they can swap that out for a Moku and do all of that in software.
Now, time is advancing very quickly here in the show today, unfortunately, because we've had some great conversations. Before we bring Matt and Mark back into the fray for a roundtable discussion, I'd like to ask you, what's the sort of cleverest use for a Moku that you've seen to date?
That's a good question. I love working in test and measurement because my stuff gets used by people much smarter than me to do things a lot more interesting than anything I could have ever thought of. What's a couple of highlights? Okay, so one that I heard just a couple of days ago, big multinational semiconductor company, they have a lot of sockets inside the Moku and probably in the SMU 4000 as well. They bought a Moku Pro, they gave it literally to an intern and said, here's a testing scenario, it takes 3 hours to run, you need to move the device under test between some different boxes and so on. What can you do with the Moku? The intern and our Python APIs took that 3-hour test scenario down to 7 minutes. And moreover, that 7 minutes, the setup was then simple enough that they could ship Mokus and have them set up in remote offices wherever the chips were, and the engineers could remote into them. So you didn't have to wait for the chips to be sent across the world. They just got plugged into literally the nearest Moku in the world, and the engineer took it from there. So that's a good one. I know we're short of time, but the one that I love is the Moku Go. Cheap, simple, robust, works on DC. There's an Australian agri-tech company who are building some essentially wearables for cows without going into details. And one of my favorite stories was, watching a pile of Moku Go's in specially designed harnesses on the back of cows, probing out this wearable as they roamed around a field while the guy on the other side of the fence was there on his laptop monitoring all of the signals in real time. So.
Oh, that sounds fantastic. I have a funny feeling I might know who that is because I was following an IoT an IoT company building agricultural sensors for cows. So we'll have to catch up later and see if we're talking about the same person. Super. Well, with that, I'll bring Mark and Matt into the group here. So welcome back, guys.
Hi.
So we have a very active audience today. I'm really, really excited. So the first one is we've got R. Bushy, and he's got a great question actually related to the SMU 4000. And he's asking, are you able to export those setups for backups or sharing?
Yep, you can. So any setups or sequence modes that you create, any sequence files, and you can export them. Our TestBridge software, SMU TestBridge, allows you to create them. Also, you can export them or import them into TestBridge. But also, you can. We wanted to make it easy for users to say you had multiple SMUs. If you create a setup in the SMU, you can then store it in that SMU, transfer it to a USB stick, and then take it onto another SMU and import that into that other SMU. Yeah, so it's very transferable. All these sequences and setups can easily be transferred between SMUs and between TestBridge
And importantly, a setup can be modified within TestBridge SMU. So if you spend a long time setting up a very in-depth setup, it's easier to modify than start again.
Of course, yeah, exactly. Now that's one of the benefits, isn't it, of having those visual environments and the tools on the computer that you can go back and put those in again. Now that's relates very much, I think, to another question here. By the way, Ben, R. Bushy says smart intern. So I think he was quite taken.
I don't disagree.
Yeah, exactly. Yeah, no, I was impressed as well. There's another one here from. Hi Annie. Annie's from the USA. She's sending her greetings. Hi Annie, thanks for joining us. There's a message here from Hamadou. And Hamadou asks, in the framework of collaborative learning scenarios where some of users don't have real devices at a distance, can we think about how to store and share instrument settings? Now that came in just as you were talking, Ben. Do you have like a portal or something where people can sort of upload their test environments that they've created for the Moku range that they can share with other people?
No, we don't yet. That kind of marketplace idea is certainly something that we're working on. But at the moment, a lot of our customers are like aggressively private about what they're doing. So it hasn't really come up so much. But certainly in the terms of collaborative learning scenarios as well, the ability for people to be looking at the same interface as their mentor, as their supervisor, as their tutor in an education scenario, and so on. Being like network native allows us to be like collaborative native. I saw this funny thing. I'm sure you've all seen it as well. People who take photos of their oscilloscope on their iPhone and share the screen. I mean, that's one thing, but I saw a guy who had 3D printed a bracket to hold his iPhone in front of the oscilloscope screen so he could take reproducible photos. That's just not a thing with the Moku way of doing things. You're always using the tool that's best for it. And if you need to collaborate, then you've got the whole like iPad suite. You can be on Zoom calls and things as you work.
That's a good point. I think Mark might be better placed than me to answer this question, but didn't they used to have like a fixture for oscilloscopes with a film camera? You used to be able to plop it on the front, didn't you, and take
you did indeed.
Take photos.
But I bet we've got one in the lab upstairs still.
Yeah, you have to dig it out. See if we can find one. We'll have a retro test and measurement show, and we can reminisce about the old beige times. Super. So Hamadou says, thank you, Ben. And Arbushi would have liked to have seen the results of that demo to see what happened after the after you changed the FIR filter. So maybe do you have some sort of like YouTube channel where you share testing challenges and how to overcome them? So maybe there's an opportunity to see a complete PID demo there.
Yeah, absolutely. YouTube.com/Liquid Instruments. We do have that particular PID demo presented in a couple of different forms at the moment. It's one of our favorite little demos to do. It works well on a booth, even if it does annoy the people at the booth next to it, as it's a little bit noisy and so on. If you're interested in more, especially tailored demos or whatever, then get in touch, and I'd love to give you a one-on-one at some point.
There we go, super. And there's the webinar coming up, as you mentioned as well. Arbushi says, thanks again. We've also got a message here from Dom Conti. Yes, love the retro stuff, so that's a big thumbs up for a retro show. We'll see if we can fit that in around. I'm planning a retro show on 8-bit microcomputers, so maybe we'll do retro computers and retro test and measurement equipment. So that's good stuff as well. Another question for Matt and Mark, or Mark and Matt, whoever feels most prepared to answer the question. Do you have any recommendations for, I don't know, books or resources around measuring and testing that you think are good for, let's say, students or people starting their careers who want to sort of get a bit deeper and understand how best to do testing and measurement?
I think I'll probably answer that. I mean, there is a huge amount of information out there. We, as a small to medium-sized company, don't have that material of our own. We have a lot of knowledge, but a lot of it is not down on paper. But there is, from, dare I say, and dare I mention, people like Keysight, there is so much information out there. Yes, the web is a wonderful thing. Everything is shareable.
Exactly. The big challenge I find is, you're right, because I do a lot of research as well for the articles that I write for Elektor. But obviously one of the biggest challenges is knowing who's correct or who's sharing information that is correct and usable, because if I go to, like you say, your website or Keysight or one of the other big test and measurement companies, they're respected companies. Anything they produce, you sort of make the assumption, well, that's probably good quality. But elsewhere, you're never really sure as you're scouring the web what the quality of that information is.
My preference is always for concise information, and there does tend to be within a lot of companies, the more pages, the better.
Yeah.
The quality of the content can easily get lost.
Yeah, exactly. Super. Now, Ben, last week we were talking to Roden Schwartz, and we got onto the topic of probes. And what sort of, obviously, when we buy an oscilloscope, a beige box, we get 2 standard passive probes with it. What's the situation with the Moku products? Are probes included, or do you just provide some cables? And do you have any tips around probe and cable selection for measurements?
Gosh, yeah, good question. So at the lower end, the Moku Go's they come with passive probes. The bandwidth of that device is 30 megahertz or so, which is easy to probe on. For the Moku Pro, right at the other end of the spectrum, where that can sample up to 5 gigasample, and you're looking at hundreds and hundreds of megahertz bandwidth. We sell optional probes there because actually most of our customers do tend to cable them into their systems. It's a bit more reliable, and at the end of the day, we do recognize that. Look, everyone's got an oscilloscope. It's just the thing that's on your bench. Then you add the Moku to kind of be maybe your daily driver oscilloscope, but certainly everything else that we've been talking about, wave gens and lock-in amplifiers and all sorts of things. And those do tend to be permanently cabled.
Right. Super. Now, Mark and Matt, having been around in this industry for quite some time, and also being at the cutting edge there, sort of developing products for customers, what are some of the most challenging test and measurement activities that you've experienced amongst your customers, and how do people go about resolving those?
Being a general purpose company, we get it from all sides, in that power is definitely going up in DC power supplies. Within the SMU, we believe that the low voltage, low current measurements are going to be a challenge that is being addressed by a wider audience, and we hope that a €3,500 entry point, and we'll be able to address that. So I think people are doing much more challenging things than used to be achieved. Like you say, sampling rates are faster, signal levels are lower. On the power side, currents are higher. So it's a real mix of stretching the envelope of general purpose. So that's our challenge, really.
Exactly.
Continue to push.
One of the things
totally
that
agree.
Popped into my mind as well, Ben was mentioning ChatGPT and the fact that you can use even ChatGPT to develop some HDL code for the Moku. I wanted to ask Matt at AIM-TTI, when you were describing how the SMU was being developed and the fact that there was this capability to measure the signal and wait for it sort of to be stable enough to be a correct measurement. When you're sort of like developing new test equipment, do you think there's an element of machine learning or artificial intelligence that's going to be built into test and measurement products in the future to sort of support the measurement process?
I mean, it's definitely possible. It's the way the world's going. So I definitely agree that that's a possibility in the future. Slightly scary one, but but yeah, certainly. I mean, this project for me was certainly an eye opener. It's not something we've done before, and it's sort of pushing our envelope of knowledge and capability. And some of the algorithms I started with have changed drastically over the time of writing them, and they've become far more than I ever expected them to be. And it's only a stage further that you start talking about this machine learning and this capability for the product to develop itself almost. But it's certainly a possibility.
We've over the years produced products called spectrum analyzers and logic analyzers and harmonics analyzers. Customers often expect analyze means give them a result. Prior to AI and where we are now, those results had to be interpreted by a human being.
Yes.
I can certainly see that may change in the future.
No, exactly. There's a company that I spend some time working with. They're called Monolith, and they support their customers with an AI platform that analyzes very complex data sets and is able to sort of search around all these multiple dimensions. You can have like 10, 20 dimensions of data, and out of it, they're able to learn very complex information about how a chassis functions in a vehicle. There's also an example of a I think it was some sort of electricity meter that needed to be calibrated, and it was able to do this calibration process much more effectively with all that data than you could even do it through a series of pre-programmed algorithms. So I think AI is an interesting point. What about you, Ben? Do you see an AI block for Moku on the horizon sometime?
Yeah, absolutely. We've already got customers who use our Python APIs to, in a testing scenario, to acquire waveforms, and then rather than putting a mask around them or trying to take a measurement out of them, they simply ask their Python-based AI model, does this look the same as my golden reference?
Right.
Yes or no? And
Yeah.
that's the pass-fail criteria right there.
Yeah.
Moving it down into the FPGA is a potentially super exciting area for us, or for someone smarter than me at least. But yeah, look, the rate at which this moves on, the speed of development in this space is insane. So yes, if I'm lucky enough to be back on the show in another 12 months, we'll think that everything we're saying here is rather passé.
Great. Well, thank you ever so much to all three of you for your support in the show today. That's about all we have time for today. So thank you, and stay in touch. And if anyone watching wants some more information, they can follow up with you with the description that will appear underneath this video once it's all wrapped up. So thanks ever so much.
The questions. Thank you.
Thank you.
Perfect. Thanks so much, Stuart. Appreciate it.
So that's all we have time for in this episode. So what did we learn? Well, the days of lugging stacks of test and measurement equipment around the laboratory are very much behind us. In fact, some of today's test tools fit quite easily into your laptop bag. And because of digitalization, these tools are programmable, allowing you to implement automated testing. This allows you to learn more about your components and circuits and generate and store large quantities of data for later analysis. If you regularly need to perform current voltage characterization on semiconductor components or analyze battery performance, it's worth investing in a source measurement unit. Today's SMUs, like the SMU4000, are easy to configure, delivering high accuracy measurements as part of an automated setup. Then there are the increasingly popular headless test and measurement tools. As they have no screen of their own, they can be brought up close to the application they are measuring. By integrating many functions that can be combined to operate in unison, they can also be an active part of your circuit, as we saw today with the Moku operating as a PID controller. Thanks to today's experts, Mark Edwards and Matthew Middleditch from AIM-TTI and Ben Nizette from Liquid Instruments. You've delivered us some outstanding engineering insights. So that wraps it up for today. If you'd like more of the same, we're broadcasting 2 episodes of Engineering Insights every month in 2023. And to keep you abreast of industry trends this year, take a look at QSPICE, our monthly 15-minute show. Please subscribe to Elektor TV Industry on YouTube and share our videos on whatever platforms you use. Additionally, you can now drop by the website at elektormagazine.com/EEI to see the topics for future shows and sign up for regular email updates and reminders. Finally, if you'd like to join me as a guest, write me an email, drop me a tweet, or reach out to me, Stuart Cording, on LinkedIn. Thanks for joining, stay in touch, and don't forget to keep asking your engineering questions.